Hi everyone, welcome to Lecture 26 on Basic Inorganic Chemistry. My name is Dr. Teresa Chimambam. For today's lecture, we will cover oxidation-reduction reactions. It is also known as redox reactions. Now we look at the meaning for oxidation and the meaning for reduction. Oxidation is the loss of electrons by an element. Reduction is the gain of electrons by an element. Oxidation and reduction occur simultaneously. Whenever oxidation takes place, reduction must also occur. So both occur at the same time. So for example, a reductant is an element or a compound that has lost electrons. So when this reductant loses electron, it will form a product, and this shows that it has lost one electron. And whenever an element loses electron, its oxidation number increases. For reduction, which is gain of electrons. Any element that gains electron is known as an oxidant. So an oxidant will gain one electron, it will gain one or more electrons, and when it does that, it will form a product. So when electrons are gained, oxidation number decreases. So redundant is an element that has lost electrons, as you can see here, while an oxidant is an element that has gained electron. That's why we have plus electron. So oxidation and reduction occur simultaneously. Oxidation is the loss of electrons by an element, while reduction is the gain of electrons by an element. When an element loses electrons, its oxidation number increases. But when an element gains electron, its oxidation number decreases. Right. From the previous slide, as I have explained in the previous slide, oxidation and reduction can properly be referred to as a change in oxidation number. This is because the actual transfer of electrons may never occur. So we can properly define oxidation and reduction as a change in oxidation number. So oxidation is increase in oxidation number, while reduction is decrease in oxidation number. Oxidation and reduction reaction is also called redox reactions. So whenever you see redox reactions, simply means oxidation reduction reaction. Okay, oxidation reduction deals with all chemical reactions involving change in oxidation number of atoms. So whenever oxidation reduction occurs, there must be change in the oxidation number of atoms. This change can be a decrease in oxidation number, or it can be an increase in oxidation number. When there is an increase in oxidation number, we say that oxidation has occurred. For instance, here, the oxidation number for sodium is 0, here is +1. So the oxidation number for sodium increases from 0 to +1, therefore oxidation has occurred. But for chlorine, the oxidation number decreases from 0, as you can see here, to -1. And when there is a decrease in oxidation number, we say that reduction has occurred. So oxidation reduction deals with all chemical reactions involving change in oxidation number of atoms. The oxidation number can either increase, in that case it's oxidation, or it can decrease, and in that case it is reduction. Okay, we have mentioned oxidation number and we have also mentioned oxidation state. So we need to know the difference between oxidation state and oxidation number. Oxidation number and oxidation state are normally regarded as the same. The reason is that it is possible for the oxidation state to be the same as the oxidation number for some atoms, depending on the type of compound where that atom is present. So it is possible for the oxidation state to be the same as the oxidation number for some atoms, depending on the type of compound where that atom is present. So let's look at the major difference between oxidation number and oxidation state. Okay, the major difference between oxidation number and oxidation state is that oxidation number is the charge of a central atom in a coordination complex. So this is the central atom and this is an example of a coordination complex. So the oxidation number for this central atom, cobalt, is 3+. So the reason why the coordination number is 3+ is because we have 1 chlorine here, 2 chlorine atoms here. So 3 chlorine atoms. So because we have So we now look at reducing agent and oxidizing agent. A reducing agent loses electrons. Remember that oxidation is loss of electrons. So what this means is that a reducing agent is oxidized during a chemical reaction because oxidation is loss of electrons. And since a reducing agent loses electrons, it must be oxidized during a chemical reaction. A reducing agent reduces another substance because it is oxidized during a chemical reaction. The oxidation state of a reducing agent increases during a chemical reaction, and the reason is because when electrons are lost, oxidation state increases. And remember that a reducing agent loses electrons, so its oxidation state increases. A reducing agent loses electron and a reducing agent is oxidized during a chemical reaction, and a reducing agent reduces another substance, and the reason is because it is itself oxidized during a chemical reaction. Let's look at oxidizing agent. An oxidizing agent gains electrons. Remember that reduction is gain of electrons. So it means that an oxidizing agent is reduced during a chemical reaction because reduction is gain of electrons, and since oxidizing agent gains electrons, it must be reduced during a chemical reaction. An oxidizing agent oxidizes another substance, and the reason is because it is itself reduced during a chemical reaction. The oxidation state of an oxidizing agent decreases during a chemical reaction, and the reason is because when electrons are gained, oxidation state decreases. And remember that oxidizing agent gains electrons, and so its oxidation state must decrease. And remember again that an oxidizing agent is reduced during a chemical reaction, and an oxidizing agent oxidizes another substance since it is itself reduced during a chemical reaction. So these are some of the uh, differences between reducing agents and oxidizing agents. We now look at examples of oxidizing and reducing agents. So these are some of the examples of reducing agents: carbon, carbon monoxide, metals, potassium iodide, ammonia. These are some of the examples of reducing agents. And these are the examples of oxidizing agents. We have potassium dichromate 6, we have sulfuric acid, we have nitric acid, we have potassium permanganate, we have hydrogen peroxide. So these are some of the examples of oxidizing agents, and these are some of the examples of reducing agents. We have looked at the difference between oxidation number and oxidation state. Now we look at the guidelines that must be followed whenever you are asked to determine the oxidation number. We start from Rule 1. Atoms in their natural form or elemental state have oxidation number of 0. So any atom in its natural form or in its elemental state must have an oxidation number of 0. What do we mean by natural or elemental states of atoms? Atoms are in their natural or elemental form if they are not combined with other elements. For example, you see H2 here, it is not combined with any other element, so it is in its elemental state. The same thing is applicable to O2. It's not combined with any other element. Therefore, all these are in their elemental states because they are not combined with other elements. Also, atoms are in their elemental state if they are not charged. If you look at these examples, H2 is not charged, O2 is not charged, and all these are not charged. So they are in their elemental states. Also, atoms in their elemental states are most stable. You can see all these are all very stable. So what Rule 1 means is that atoms in their natural form have oxidation number of 0. So the oxidation number of hydrogen here is equal to 0. The oxidation number of oxygen in O2 is equal to 0. The oxidation number for Br is equal to 0 in Br2. The oxidation number for iodine in I2 is 0. The oxidation number for N in N2 is also 0. So atoms in their natural form have oxidation number of 0. So we go to Rule 2. Monoatomic ions have oxidation number equal to their charge. So when we talk about monoatomic ions, we simply mean single atoms. Examples are sodium plus, so it is a monoatomic ion because it's only sodium, it's not combined with any other element. So monoatomic ions have oxidation number equal to their charge. So Na plus has +1 charge, K plus has +1 charge, Ag plus has +1 charge, Cu plus has +1 charge. The same thing is applicable to Cl minus. Its charge is equal to its charge that is attached to the element. So Cl minus has -1 charge, Br minus has -1. Same thing is applicable to this and this. For Ca2 plus, its charge is 2 plus. For Cu2 plus, its charge is 2 plus. For Al3 plus, its charge is 3 plus. And for N3 minus, its charge is 3 minus. So monoatomic ions, such as all these examples that we have here, have oxidation number equal to their charge. We now look at rule 3. In compounds, fluorine is assigned a -1 oxidation number. For example, in this compound, F has -1 oxidation number. So whenever F is present in any compound, its oxidation number is -1. Oxygen is usually assigned -2 oxidation number in any compound. For example, in water, oxygen is assigned an oxidation number of -2. That's why water is neutral, because -2 plus 2 from H2 is equal to 0. But in peroxides such as H2O2, Ba2O2, Na2O2, oxygen is assigned an oxidation number of -1. The reason why oxygen is assigned an oxidation number of -1 in peroxide is because the charge of the compound needs to be 0. The overall charge needs to be 0. So in H2O2, if you assign oxygen -1, so there are 2 oxygen atoms, it will be -2. And for H2, we have +2. Then this is balanced. The charge will then be 0. But if we had assigned oxygen -2, it will mean that this compound will not be a neutral compound, because then we will have -2 times 2 will be -4, and -4 will not balance +2. So this is the reason why in peroxides, oxygen is assigned a -1 oxidation number so as to balance the overall charge of the compound. So a peroxide is any compound that contains oxygen to oxygen single bond. So only in peroxides that oxygen is assigned an oxidation number of -1. And the reason is to balance the charge of the compound to be 0, because you want the overall charge of the compound to be 0. That's why oxygen in any peroxide like BaO2 or Na2O2 is assigned an oxidation number of -1. We now look at rule 4. When oxygen is in binary compounds with fluorine, it has a positive charge. Example is in OF2. In OF2, the oxidation of oxygen here is +2. Remember that the normal charge for oxygen is -2. But whenever oxygen is in a binary compound with fluorine, its oxidation number is usually +2. And again, the reason is to balance the overall charge of the compound. So here, F has a negative charge. Because there are 2 fluorine atoms, it will be 2 minus. So the only way to balance this compound is for oxygen to have a +2 charge, so that +2 and -2 will be equal to 0. So this is the reason why oxygen is assigned a +2 oxidation number whenever it is in a binary compound with fluorine. The reason is for the overall charge of the compound to be 0. Hydrogen is usually assigned a +1 oxidation number, as we have seen earlier, except when it exists as the hydride ion. An example is H minus. Whenever you see H minus, it means that hydrogen has oxidation number of -1. So in this case, rule 2 applies. So the charge that is attached to H will become its oxidation number. But apart from this, the usual charge for hydrogen is always +1. But when you see H minus, rule 2 applies, and that rule 2 says whatever charge that is attached to that atom will become the oxidation number of that atom. So here, hydrogen has an oxidation number of -1. Rule 5. The sum of the oxidation numbers in a neutral compound is always equal to 0. Examples of neutral compounds are water, H2O, NaCl, NaOH, H2SO4, and many others. In water, for example, we have H2O, so each H has a positive ion, and oxygen has 2 minus, so 2 plus 2 minus, the net charge is equal to 0. For sodium chloride, sodium has positive, chlorine has negative. Positive, negative, net charge is equal to 0. For NaOH, Na has positive, OH has minus, positive, negative, net charge is equal to 0. So the overall net charge in every neutral compound is equal to 0. Rule 6. The sum of all oxidation numbers in a polyatomic ion is equal to the charge on that polyatomic ion. An example of a polyatomic ion is SO4 2 minus. Polyatomic means more than one. Poly means more than one. See here, you have sulfur and you have 4 atoms of oxygen. So here we have more than one element that is present. That's why it's poly. So this rule states that the sum of all oxidation numbers of the different elements that are present here must be equal to the charge on that polyatomic ion. So here we have one sulfur atom, that's why we have one here, multiplied by 6, that's the oxidation state for sulfur, plus 4 because we have 4 oxygen atoms, multiplied by -2. Oxygen has oxidation number -2, so you must equate it to -2, which is the charge of this polyatomic ion. So in this rule says, it states that the sum of all oxidation numbers in any polyatomic ion, as I have shown here, must be equal to the charge on that polyatomic ion. So in this case, it must be equal to -2. So the same thing is applicable if you have a polyatomic ion that has an overall charge of 3 minus, you must equate all the oxidation numbers of the individual elements, you must equate it to -3, assuming you have -3 as the charge of that polyatomic ion. Okay, let's look at some examples on how to calculate oxidation numbers. So if you are asked to find the oxidation numbers for potassium and fluorine in Kf, so K has oxidation number of +1 because potassium has a positive charge. So remember, the charge of a monoatomic ion is equal to its charge. So the charge for K plus is equal to +1, and the charge for F minus is equal to -1. Hence, the oxidation numbers are +1 and 1 for potassium and fluorine, respectively. So we have a look at another example. Let's have a look at another example. Calculate the oxidation number of nitrogen in nitrate ion. We apply rule 3, which tells us that oxygen has an oxidation state of -2. So N plus 3 multiplied by -2. This -2 is the oxidation number for oxygen. And we put 3 here because we have 3 atoms of oxygen is equal to -1, since the overall charge is -1. So N minus 6 is equal to -1. Therefore, N is equal to +5. So N has oxidation number of +5 in this compound. So these are practice problems for you to practice and familiarize yourself on how to do this type of calculation. Okay, these are the answers to the practice questions. So you solve them first and then see if you will get the correct answers. Right, so this is where I'm gonna end for today's lecture. Please like this video and subscribe, and I will see you in the next lecture. Bye.